Good evening, everyone. My voice is getting recorded. Yeah. Good evening, everyone. Welcome to today's problem solving section, week 11, course digital VLSI testing. So today we will see about the network on chip testing. Previously, we covered on the system on chip testing and some portion of the network on chip. What is the network on chip and why we need a network on chip? So this class we will cover on the network on chip completely. And next class, our last class will be on the memory testing. So in the SOC we had for the system on chip, we said that we have one chip. In that we have say one core, core 1, core 2, core 3, multiple cores. Previously, first we said the board level, where we saw the board level testing, where we have one PCB board. In that we have one say chip 1, chip 2, and chip 3. And we said that this off chip communication is slower than this on chip communication. So we fabricated the cores and interconnected them and formed the SoC. Now, if we have multiple cores, then we can either have a point to point connection, or which will be having so much of routing. And so, can we have a shared bus architecture? This was our next architecture that we saw. If we have shared bus, then again we can't go on adding the number of cores on the shared bus. So it will degrade the performance of the bus. Then from this we came to network on chip. This is how we started. First we started with the board level testing, and then we came to SoC testing, IEEE 1500. Then now we are in the like from this we said these are the possible way of interconnecting between the cores. Then we came to the network on chip based design. So testing the embedded cores in the NOC. What is network on chip means? I have 4 routers. So this is the connection. Like every this space we have one router. So 4x4 routers are available, and now every router is connected with one port. And say this now for testing, this is we connect to an automatic test equipment where this is giving the patterns say to this port. Next, consider this is connected to one port, and say it is connected such that the responses are collected back to the AT from this port. Say AT has another channel. So here we have one port. Now this portion, say here we have one port. Now this port is again giving back the responses to the AT. So now if we say that we are following the XY based routing, that is we travel through the X direction first, then the Y direction in this way of routing. Say now I am testing this particular port to this port point. Then I have to travel in the X direction and then the Y direction. We have come to this port where we can collect the output back to the AT for analysis. Now say this port, only this portion which is highlighted in yellow, I'll just different color. So the portion which is highlighted in yellow are used for testing of this core. Now for another core can be parallelly tested if the routing resources are not conflicting. So like X, Y, I'm coming to this and it is back to the AT. So you can see the green line and the yellow line have different path for applying the test pattern and getting back the test responses back to the AT. So this two can be tested parallelly if AT is having two channels. So this is VLSI. But if the uh, routing, like this routing was not possible and we had to, somewhere we had an overlap, such if there should not be any overlap. If there is an overlap, then we cannot do testing of that parallel. So with this, I hope what is this network on chip is clear. So the first point, reuse of the on-chip network on testing. So if you see NOC, we are adding for the connecting between the cores. So we are not, then we are paying for NOC for the interconnect, not for the functionality. So already this is an overhead. So we cannot add, like adding more testing, adding a testing architecture for an NOC will be an adding another overhead. So can we reuse this on-chip network itself for testing? And so for that we need test scheduling and test access methods and test interface. So what is the test access method and the test interface, and what are the efficient ways of reusing this network? And similarly in the SOC testing, we have already seen the power aware and the thermal aware testing. Okay, now coming to the network on chip, current design methodology, system on chip. So yes, if we have a system on chip, we have multiple cores, say one core for CPU, memory array, embedded RAM, IP core, and some user defined logic, UDL, self-control logic, interface control, DSP, core, and legacy core. So now how can we connect between this core? So interconnection scheme, we have said that we will have a shared bus, but this shared bus, we cannot go on like adding cores. It will degrade the performance of a bus. And for dedicated connection, you can see that there are multiple routing required for this. If the number of core increases, then the number of interconnects will go up significantly. So we are saying that there is a need for a network on chip. And design communication infrastructure is becoming a new bottleneck. Like we have multiple cores now, the communication between the two cores are becoming a bottleneck. So because of that, there is a wire delay. There is an issue with signal integrity, power dissipation, area versus speed. Now, what is this? So signal integrity. Wire delay means this interconnect delay. Now we are coming from this shared bus to this NOC. So in the NOC, we need to test some. Okay. So now for the signal integrity, say we have a serial communication. So there is one link and data will be transferred serially. If we have a parallel communication, then we will have multiple parallel, each transferring on one bit. So this will be giving parallel communication. So, but there is an issue of crosstalk. Say this. So there is an issue of now in the parallel. If we are using say faster communication, say with high speed, we are able to transfer data with high speed because say we have 5 buses parallelly running, then we can transmit 5 bits at a time. Here only one is possible, but here there is an issue of crosstalk. So we have that model of aggressor. Like now, what is the signal integrity means? If we have two signals and say this line should be always 1, but because this line makes a transition from 1 to 0, this line makes a transition from 1 to 0. Because of this, if the lines are closer to each other, instead of staying in 1, it goes to 0 for a short period of time. This is also known as glitches. And say similarly, if this node has to go from 1 to 0 to 1, and this transition, this has to be stay in 0, it goes momentarily to 1, and this duration or this is glitch, how long the glitch is, it will depend on the coupling strength. So this is the signal integrity issue. And power dissipation, the power is more. I think that is covered in next chapter. I'll just briefly say for the power dissipation. Now, before like this is the core. In the core, a portion is consists of the router. Now, when before in the functional operation, when this core is not used, we can turn off this core. Like when this core is ideal for the power like we can turn off this core. But now, say this place, now we have to communicate. So this bit has to encode this. So for testing of this, say this core or any one of the core in this yellow line, highlighted line, all the cores should be on because all the routers are in use, as the router is embedded inside the core. So this increases the power dissipation in the test mode compared to the functional mode of operation. So next is the new interconnect schemes are needed. So actually this issues test of the SOC. This one I just wanted to discuss because here we saw that we have to consider the thermal and the power aware testing in SOC, NOC also it is needed. So this is why it is needed in NOC. Next one, test of the SOC has well understood. So we have seen that for the test of the SOC, we need the TAM architecture, test access mechanism, and the wrapper design. We have to perform the test scheduling and IEEE 1500 standard. So test needs dedicated hardware. Hardware for mission mode communication cannot be used for testing. So NOC based testing. So this we have seen that this is the router. Each router is connected to one core. And say our tester is providing two input lines. Say SI1, SI2, and is supporting one output. So SO1. So if we follow XY routing scheme and say we want to test this particular code, so the input should come from here. If we choose to test from this or in this path, after testing this code, response should go by X and then X to the tester. Another possible method could be if coming from SI to from X directly to the code and then again X to the SO. So NOC based testing, possible next generation SOC paradigm is the network on chip. So the design, it gives high performance, high bandwidth, low signal delay, reasonable overhead, suitable for large number of cores, because we said that if we go on adding more number of cores in a dedicated or point-to-point network, then the interconnects will go on increasing. And when we have the network system on chip, the area is also limited. And when we have shared bus architecture, we can't go on adding the cores because it will degrade the performance of the bus. So NOC is suitable for large number of cores. The network design is versatile. Methodology for next generation VLSI design. So for the testing part, so test of NOC has not received much attention. Here we have to test the core. We have to test the router and interconnect. We have to test the we have to design the test wrapper for it and then perform test scheduling. So previously we were doing only the core testing, but now we have to test the router plus the interconnect. And there is no need for dedicated TAMs. So we said we will use existing because already with NOC we are adding the extra overhead. And network can be used for testing. So what is the network on chip? Say we have this interconnect. And then here we said we have a router and it is connected to a core. So we need to test the core, we need to test the router and the interconnect. When it was SOC testing, we had to test only the core. So NOC based system. So packet switching, bidirectional channel, 2D mesh, XY routing. So what is packet switching? Between say this and this, we have to communicate between port 5 and port 10. We pass the message in packets. So the messages are passed as some packets. So here we perform the packetization. Okay. And then we add the some start bit or the demarking bits. From this, the code which is reading it has to unpack that and read. So we have to perform the depacketization. So XY routing, uh, if you see, meaning to say that it's communication will we go to X direction first, then it will go to the Y direction. Channel routers used as TAM. So the test access mechanism is this routers and the channels and input output port associated with the port. Port channels are assigned a time tag. So in a testing, okay, if say we have okay, test scheduling problem. So how to assign IOs and channels to each core for testing such that the overall test time is minimized. In an NOC systems, using dedicated routing path given NC code, NI inputs, NO outputs, routing algorithms and the network topology determines an assignment of cores to input or output pairs and a scheduling such that the total test time is minimized, equivalent to the resource constrained multiprocessor scheduling problem. If if the number of input or output pairs is greater than or equal to 2, then it is an NP hardware. Before, if we had a link uh, between say we had a TAM of width W is equal to 64 bit, we were able to say have a variable width for say core 1 and core 2. Now, if we have a router and we have a link, we have another router. So if this link is say 32 bit or 64 bit or 128 bit, this has connected to a core, and this core is having a fixed wrapper design. So test scheduling optimal solution using integer linear programming ILP. Problem can be solved exactly using an ILP model. Large number of non-zero constraints, CPU time is prohibitive. Can be simplified using enumeration. Enumerate the assignment of the cores to IO pairs. Number of constraints reduced. A few seconds for small instance with smaller number of IOs. For large instances or large number of IOs, CPU time is still high, probability high, not suitable for larger designs. So next is the heuristic algorithm where we sort the cores and IO pairs in decreasing order of testing time. Permute cores and IO pairs. Assign cores with high priority to free IO pairs. Check the resource conflict using the time tab. IO channels cores. The complexity is big O and C power m. CPU time a few minutes for all benchmarks. The test access method and the test interface. Problem targeted test access scheme for testing routers at NOC level. Possible hardware overhead. Efficient test scheduling that can handle both routers and the embedded functional cores. Test access method. Slide did I skip? I think I have missed some slide. Okay. In the testing, if we have a non-preemptive way of testing, then the test should complete that particular test. Then only it can go to the next session or the next test session. So it has to complete the like if it is started testing a particular core with particular thing, it should complete. Then only it has to go to the next thing. So the test scheduling, like that routing path, is completely reserved for that particular test session. Once it is completed, then only we can go to the next step. So I will take one empty slide here. So if we consider this as the network on chip, and say here we have a core router 46. Say here we have a core 10 and a router. Say here we have another core 2. Say another core and router 5. So from here we have an output, and from here an input. So IO of the 18. So now we can say that 2, 5 is the input output pair, and say here also we have one input and one output. So 6, 10 is another input output pair. So with the IO pair, the path will differ. If the if we have the path which are not overlap, like in this case, say this is the code to be tested. So input will come from this router, say output is coming from this router. It should also be connected to some router. Now this path is reserved. If the paths are non-overlapping, then we can perform the test parallelly. In parallel. So SOC based problems, we have seen that SOC, those were also solved using the ILB base. So say this is the particular, and we are performing a testing. So this particular path is reserved for testing. Now normally in the functional operation, we don't reserve this like this any path as we are doing it here. So now say if this has to do with some communication, and say this is performing some communication, then there is a competition and there occurs conjunction. But we reserve during the testing, which we don't perform during the functional operation. So in this case, if you see the number of input is 2, which is 2, 6, and the number of output is also 2, which is 5, 10. Now, how to perform this testing? Just small example. I'll take one more slide. Say we have the course C1, C2 till up to C10, and we have the IO pair, say I1, I2, and I3, 3 IOs. Now the permutation and combination, say we say that this particular combination we will test C5, C6, C10, then we will test C9, then C7, and then further. And for IO mapping, we say that say first I2 will be called, followed by I1, I3. Then to test C5, it will resolve this IO1 and IO, not IO1, this IO2, and perform the testing. Similarly, for C6, it will take I1, like whichever is, and then further whichever is 3. Now, in this network on chip, we said we have a router and we have a port. So we need to test the link, the core, and the router. Now let's just ask one simple question. To test this router, the test pattern has to be applied. So from where can we generate this test pattern? Should it come from the ATE or generated at the side. So this is the question. Then this will add an overhead, and also now we need a response analyzer. So again, should it be inside or should it go to the ATE? So this will, okay, we have applied the test pattern. See, now the response. So this response, should it be analyzed inside a router or should we take back to the ATE? So router should support the multicast, but the router in the on chip, the router is in the on chip are generally simple, basic, not like having a complete computer as a router. So what is test access mechanism? So we have to we said that without adding the extra overhead, we will be reusing the network resources for test access. Test data and test control delivered in packet. Responses can be processed by the ATE or on-chip. So now the test data are delivered in the packet, that is from the ATE, and the responses are going to the ATE or it can be analyzed in the on-chip. So if we have a multicast basis system, where multicast means we are able to say 1, 2. We have 2 input channels and 2 output channels. So first we will test 1 and this to 4. Next we can multicast this. So these are connected to it. So it will receive the pattern. Now to the 2, these are the cores which are connected. So it can receive the pattern and it will be tested parallelly. Next to this 3, this 4 is connected. So it will be tested parallelly, followed by this 5. Similarly, if we said that the on-chip routers are very simple and basic, if the this can be done only if the router supports multicast. If the routers are like as they are basic, so they are only supporting the unicast. So only two cores can be tested at a time, because as the response, like we test this 2 core, we can collect the response in this 2 core. That's it. Next, it is coming to this 2 and response are collected. Now this is getting the patterns and response. Next, this and this, level by level, and followed by this one, and the 6th, these 2 cores are getting the test responses can be handled on chip. So we have said that we have a router and we have a wrapper, and this is multi-input signature register. So this can perform the analysis, so minimum overhead probability of mixing, or we can have similar to the previous work, faster with aliasing. So we can have some comparator and then perform the comparison. test wrappers on top of the 1500 compliant wrapper can wrap both router and port. Unpacking or packing mechanism reuse fuel from the mission board. So this one, whatever the test inputs are there, it comes in packets, so which are unpacked, applied to the for testing of core as well as the router. Both we have to do. So both are wrapped with the 1500 wrapper cell, and then we get unpacking of the response. Like again, we pack the responses, and then if needed, we can apply to the next processing code, or we'll go back to the AD. So if we want, we can add even the bypass and then test the next code. And say if I have a pattern P of say 32-bit, which is connected between this two, and we have the link which is of just 16-bit. So we need to do two successive transfer. So in one, so we define another parameter which I think we will see in the next slide, which is fleet, which is the in one clock cycle how much data you are transfer. So usually we have this as fleets per packet, and usually it takes 1 to 5 cycles to reach the router. This concept of fleet. So test wrapper, this is in the mission mode. Like we perform the unpacking, which goes to the core and back to packing, and then the router, whatever is the data, can get to the router, go to the unpacking, go to the core. The data back goes to packing. It is packed and the router transfers to the next adjacent. So this is how it works in a mission mode. So integrity test scheduling based on network reuse and dedicated routing path. Permute cores in the order of test time. Permute all in input output pairs. For each permutation, find free IO pair. Check for resource conflicts. Schedule a code. Routers on a path should be all tested before functional operation on that path to be tested. Routers can be tested concurrently with the cores. At least one pair of should be used for one IO pair should be used for router testing at any time. So whenever we are testing, it is attached to a router, and this is router. So first we need to test the router, then the core. And also we can perform the testing concurrently. So integrated test scheduling. So this one we have already seen for the multicast example. From this, it was testing this, and then whichever port is connected, and then go to the next level, and then finally this one. So you can see that So here and here there are two IO pairs. So after these routers are tested, one of the two IO pairs can be used for core testing. So this is for testing of the router, and we have two IO pair. After this, we can use this any one to test the core. So first we did this for the router, and then we said we will go for the core. Any one of IO. So we said that here there is no variable dam width. So which is variable dam width is not possible in the NOC. Variable dam width is not possible in NOC. Let's say W is equal to 32, where W is the channel width. And W dash, which is the wrapper scan chain. Say it is 8, then the N is equal to 32 divided by 8, which is 4. So what is the fixed? So we said that only fixed width is possible, so not fully utilized. So if we have 16 is the channel width, and say only 8 bits we want to transmit, then the rest of the 16 are going to be unutilized. So this formula we have already seen. What is the flits and flits per bit? So utilization of the ideal channel width, variable on-chip test clocks. Use faster wrapper test clocks on ports with ideal channel width. Channel width W, wrappers can chain W dash, and flits can be transported in parallel to core in one clock cycle. Additional cores can be selected to further reduce test time. Utilization of the ideal channel width. So we can have, I said that, faster on chip clock. So we can select between which clock we want, either the faster or the slower clock. And based on that, say this is right now this multiplexer select between this output and this output of router. Similarly, this mux select between this and this output, which is applied. Say this is for say some bypass register or some testing of this code, and which goes back to this multiplexer, demultiplexer. So again, every core is wrapped with the wrapper cell, and this is for the network on chip. So we have router, interconnects, and the core. Channel width utilization under power constraints. Variable on chip test clocks use slower wrapper test clocks on cores with high power dissipation. So we will use the slower clock for the high power dissipation, and no change on the wrapper design. Physical channel is viewed as n virtual channels. Now this is the clock. Now wherever A is packet is available, there the test clock of the core A is 1, and again here A is 1. I think this is the time for without violating the setup and the hold time. And wherever B, we have the test clock for the B, and whereas for the C, test clock for the C. And this is the tester clock. Power aware test scheduling. Variable on-chip test clocks in MSC. So N cores tester clock FT, faster on-chip clocks 2FT, 3FT, etc. Slower on-chip clock FT by 2, FT by 3. Determine a clock for each core such that no network resource conflicts, system test application time is minimized, power constraints are not violated. So why we have specifically mentioned the power constraints are not violated, this we have already seen, we will again discuss. With the IO, it has to also choose the clock and such that it is like not putting all the traffic, so without violating the power and without getting any traffic resource conflicts. If we have a network chip means we will have a router within this code in the same die, not die, sorry, in the same time. So now even though this is not tested, say this is connected to this IO and we are testing currently this route core and it has its own router. This is connected. So for this testing, we are getting in the inputs this core, this router has to pass this patterns here. So during testing, say this is core 1, core 2. Core 1 should also be on. So this is ideal, not we are not testing the core 1, but still it is to be on because it is in the routing part. So power management is for now considering this like complete this style and this style. Previously, in the functional operation, if this was ideal, we could have off this and only this could be on. But in testing, both are on. Power aware test scheduling. Each core associated with a set of on-chip clocks. Each clock corresponds to power Pij and the corresponding test time Tij. The selection of clock for each core controlled by a priority calculated from del P by del T. More than one core user use slower clocks to utilize virtual channels. Use a dedicated routing path. Power constraints are evaluated. Thermal hour test scheduling, high power density causes hotspots. Now, existence of hotspot may increase the test time because of the thermal unbalance. Layout redesign is not possible. So if the layout is generally like optimized for the design and not for the test. For the design means it's optimized for design based on which module communicate which modules require to communicate. They are put close, but for testing, they may be consuming like more power. So for testing, we cannot say that we want to keep them far so that we can avoid the hotspot. So we can't say that we need a different layout. So this is not possible. And if we have the larger thermal variation will increase the delay more. So what is the method? Can we remove the hotspot and can lead to thermal balance and reduce the test time. So say we have 5 lines using this aggressor. So this line is the victim line and this lines this 4 lines are the aggressor or aggressive and this line is the victim line. Now if this has to stay at the 0 because of this neighboring aggressive lines, it goes to 1 for a small duration of time. This is called as glitch. When we have high frequency, like normal operation, we have a capacitive coupling and say in the gigahertz of high frequency, there starts the inductive coupling also. This leads to the crosstalks also. If we say there are only 3, like 2 aggressive lines and 1 victim line. This can also cause the delay variation in the sense, like meaning to say that this is the time it requires to go to 0. But say all the other lines are, this line we are trying to discharge it, other lines are 1. So it may take little longer or to discharge. But we also have, I need one more slide. Positive glitch. Say this 2 lines and this is the middle line, a victim line. This makes a transition from 1 to 0, 0 to 1, 0 to 1. So this line also makes a transition. So this depends on the amount of coupling, also known as positive glitch. Now if we consider there are 3 lines, all of them have to make transition to from 0 to 1. Before it was taking a time, like say charging time this much. Now it is charging faster. So we are getting some speed up. Variable clocking in test section still rely on using multiple variable clocking for thermal management. clock assigned to each core can be varied during test application. A more flexible scheme, more efficient thermal management, extra test control. So variable clocking in test section, say we needed this much time, this much if we are using in the clock frequency, like this much clock frequency, then it is thermal safe. So here this much we are not utilizing it. So can we increase the clock frequency here after this core 1 testing such that we can reduce the time. So now T2 is less than T1. Thermal safe constraints are not violated, but the test time is reduced. Next scenario. Say here we observed that the thermal safe constraints may be violated. So it's going above the thermal safe constraints. So for that case, we can reduce this and run it with a lower frequency and shift this core 3 here. Give this portion to core 3. That is done here. The timing is equal, T4 and T3 are equal, but the thermal safe constraints are guaranteed. And test time is not compromised. So, any doubts still here? So this clock reuse. So the PLL phase lock loop generates multiple clock frequencies. This multiplexer selects the one frequency and is applied to the port. So unpack reuse. Test control can be carried in packet. Clock varies only when the test of a core finished or started. So for one complete like test of the core, we are saying that we are going to use particular frequency. Problem formulation, test set information of core set C, NC core, NI inputs, NO outputs, set of on-chip variable rate clock, set of thermal parameters P thermal, chip of floor plan, and maximum temperature TTH. Determine first clock variation of each core during the test application. Second, test scheduling of the cores on IOs and channels such that test application time is minimized. Maximum temperature not over TH. On-chip network testing. Testing of the interconnects infrastructure. So first we have to test the interconnect, then the router, and then the core, and the testing of the network interface and integrated system testing. Unless on-chip network of an NOC has been completely tested, it cannot be used to test the embedded cores. Before also we said that first we have to test the router, then the core. Testing of interconnect infrastructure. Interconnect testing has been discussed in many papers. This discussion is mainly based on the well-known maximal aggressor fault model. Apply identical transition to all wires except the victim line to create maximal integrity loss in the victim line. So we have 6 crosstalk errors in the victim line. They are rising, falling delay. So that we have seen rising and falling delay. So positive or negative glitch. Positive glitch we have already seen. And rising and falling speed up. So here when we were discussing, we have seen it takes a longer time or faster speed up, and then the positive or negative glitch like the speed up. So this thing, so we have total 6 fault, and total if we have n number of interconnect structure with n lines, so totally we will have 6 n fault to be tested. You see the 6 n 2 input vector test pattern. What are the 6? Rising, falling, delay. This is 2. Positive or negative glitch, again 2. Slower or speed up, rising or falling, speed up. The first one she said longer is for delay, positive glitch and speed up. All the 3 we have discussed. Self-test structure. A pair of test generator. This is the TDG, test data generator, and the test error detector TED is inserted to each set of interconnect between 2 router switches. So we have a test data generator and the test error detector. So set TDG and we perform the broadcast, and the test error detector reduces. So next we have the GTC, we will see this, which is the global test controller. So test is called point-to-point MAF self-test. Test patterns are launched before line drivers and sampled after receiver buffers. Highly parallel testing if power consumption is within the power budget. Test application by unicast. So MAF test patterns can be broadcast to all interconnects by the test packets with only one TDG. So we have one TDG. We said that this GCT. If you want the global one, that is global test controller. So this is like broadcasting, and say this interconnect we are testing. So we get to this detector, and similarly let's say from here to this detector. So only one set of interconnect between a pair of routers can be tested for each test pattern broadcast. So we are broadcasting this interconnect we tested. Next, this interconnect we are testing. A global test controller, a GTC, and their TEDs are required. So what is TEDs? We have already seen in the previous slide. Test error detector. Test application by multicast. Test packets are broadcast to interconnects of all different pairs of routers to achieve maximum parallelism. Multicast is a good compromise between test application time and hardware overhead. Point to point or the unicast test method has the smallest, like point to point as the smallest, and the unicast has the largest test application time, but the largest point to point has the largest hardware overhead. Unicast has the smallest hardware overhead. So point to point, just write it in one line. Uh, and next is unicast. In terms of time, this is small, this is large. In terms of area, this is large and this is small. So there is a trade. So testing of routers. Routers are used to implement functions of flow control, routing, switching, and buffering of packets. So routers have got a good amount of logic. But one thing is that all routers are similar. So router testing can be treated as sequential testing by taking its special property of regularity, because all routers are similar. Test patterns broadcasting can be applied to reduce the testing. Testing a router consists of testing the control logic, that is the control logic, which includes this routing arbitration, and the flow control, the router and the switch, the flow control module, and this FIFO. This flow control module, there should be some flow control module included here, like will be there. Control logic can be tested typically sequential testing methods such as scan testing. FIFO test is to configure the first register of the FIFO as a scan register, and the others can be tested by the scan register. The other, if we have some memory, we will be using the memory testing, which we will see in the next class, next week class. So what the router testing consists of is, it's a heterogeneous testing. Here you can see the switch. If it is pure combinational logic, then we can test using the combinational ATPG. And say the routing and arbitration as both the logic, then such sequential ATPGs can be used. Flow control modules, like at the primary input, here there are the flow control inputs module. Testing all routers. Since all routers are identical, can be tested in parallel by test pattern broadcasting. Comparators is implemented by XOR. It also supports diagnosis. Router test wrapper design. IEEE 1500 complement test wrapper is designed to support test pattern broadcast and response evaluation. So say this as the SI. This, I think we have already seen functional outputs, functional inputs, and now we have the router and the functional port for router. So say we are testing this, some the response are collected and goes to this SI. Router test wrapper design and test. For example, all SI1 chains of this router share the same test set of the pattern. So this is the SI1. SC1. This is the SC1. This is the SC1. So for all the N as the same SC1, so share the same test patterns. Similarly, all D in 0, that is D in R0, R of 0, D in R of N of 0. Data inputs of this router share the same test patterns. The wrapper also supports test response comparison for scan chain and data outputs. Diagnosis control blocks can activate diagnosis. Small hardware overhead, about 8.5%, and small number of test patterns, several hundreds, due to test broadcasting. Small test application time, several thousand test cycle using multiple balanced scan chain and test broadcasting. This method is scalable. So with this we will conclude. The concluding remarks are the state-of-the-art technique for SOC testing has been described. Module test technique for digital mixed signal and hierarchical SOC must be developed further to keep pace with the technology advances. Test data bandwidth needs for analog cores are very different from the digital cores, and unified top-level testing of mixed signal SOC remain a major challenge. Research is also needed to develop wrapper design techniques and test planning methods for multi-frequency core testing. Revolutionary RF interconnect technology might emerge to address future SOC testing. So, till here, any doubts? Next, we will solve some of the previous year questions. So, what are the advantages of NOC over SOC? It gives higher bandwidth, low signal delay, better suitable for larger number of cores. So, answer is all of them. Going to the next question. Multiple bus architecture contributes to low area and has low speed. We said multiple bus means speed should be high, so it is not the correct answer. Speed is high, but area overhead will be more because interconnects and routing will be more. So it has high area as well as the high speed. Select the incorrect statement. Parallel communication with lower data rate can be can be faster than the serial communication with higher data rate. This is also correct. Parallel communication cannot have high data rate as it can introduce crosstalk between the multi-parallel channels. This is also true. Signal integrity comes at a state when a signal switching of a channel introduces a glitch in the neighboring channel. This is also true. So the answer is none of the above. Next, select the incorrect statement regarding interconnection schemes. The performance of the shared bus architecture suffers as a greater number of cores are connected to the same bus. Yes, we have seen that the performance of the bus will degrade. We said with that. So dedicated connection is also known as point-to-point connection. This is also correct. Dedicated connection is relatively cheaper. No. Point because we need dedicated means point to point. So every core has to be connected to the every another core, which is like not relatively cheaper. It's has high area overhead as well as high speed. Point to point connection requires large number of interconnects. This is correct. So the incorrect statement is C. So the next question we will see. Question 5. Which of the following NOC testing step was there in case of the SOC testing? So it is the testing step. So between these two, we have to select whether it is a router or interconnect testing or core testing. So for SOC, we did the core testing, and for the NOC, we need router and interconnect testing. So option D. Next question. Select the incorrect statement regarding the reuse of NOC as test access mechanism. Which of the following statement is false in the context of the reuse of NOC as test access mechanism for the embedded course? Testing time of the system increases. This is false. On-chip routing resources limits the NOC reusability. True. Because NOC has a TAM. Feasible test time can be achieved using efficient test scheduling algorithm. Yes. Testing time of the system decreases. So option A is the incorrect statement regarding the NOC as a TAM, test access mechanism. Next question. Select the incorrect statement regarding the testing of routers. So it is given that option C. XOR gate comparator lacks diagnostic capabilities. But in the slide, we have seen that it can support diagnosis. So this option is incorrect. Next, we will read. Scan testing it is utilized to test control logic. This is true. And test pattern broadcasting helps in testing all the routers in parallel. So this is C is the incorrect statement. So the next question, router testing considers. So we said that the flow control module, arbitration module, and the FIFO. So we need to test everything. Next question, select the incorrect statement regarding test scheduling. Resource conflicts has to be checked. We have to check the resource conflicts for scheduling. Before testing the functional cores, routers on the path have to be tested. First the routers, then the cores. True. For routing testing, at least one IO pair has to be used all the time. It is like first we reserve it. So yes, routers and cores are tested separately. We said that routers and core can also be tested concurrently. So this option is incorrect. Next question. Select the correct statement regarding ILP based and heuristic based resolution of NOC testing. NOC test scheduling. ILP and heuristic based solution deal with only integer values. No. ILP based solution works better on relatively large circuits. No. It was there in the slide. Heuristic based solution can be achieved at the cost of huge CPU time. Whereas the ILP-based solution can be achieved very fast. Heuristic-based solution reaches near optimal result, while ILP-based solution reaches exact optimal result. This is true. So option D is the correct answer. So next we will see uh, one more topic. So if no doubts, we will proceed with some diagnostic flow. So what is this diagnostic flow means? Say we have a test CUD, which is circuit under diagnosis. So we have a failure log. Say any circuit which has three inputs A, B, C, and the response say it is D. In this failure log, for this pattern, it is passing and giving output 0. For say this pattern, it is giving output 1 and passing. For this pattern, it is giving an output 1, which is a failure. So we need to give this to a diagnosis software which says that which fault is faulty. So say now for this will have a fault dictionary. Say this particular fault is diagnosed. Like a chip is failing for this particular pattern, then it is which fault is responsible for that. So in that we will have say the fault dictionary. Say fault 1, like A, B, C, and the response D. So say this fault 1, for this patterns, it gives a failing pattern for this and failing pattern for this. This is correct. It's instead of 1, it is 0. This means this pattern output is not obtained, like failing pattern. So for the fault 2, similarly, if we draw, if we have that, so this needs fault simulation to obtain this fault dictionary. Say for this particular fault, the same three patterns we apply and we simulate it, and we observe that this pattern is failing, but other two patterns are correct. For the fault 3, we observe that only this pattern is failing and this. So this failure log resembles the fault dictionary of the fault 3. So the fault 3 is diagnosed. So we have the test failure. Defined, like represented as TF, or the failure log. So the failing patterns and failing pins of a defective CUD, that is circuit under diagnosis, and observed on the tester. So this is on the tester. Next is the simulation failures, which is denoted as SF. So the failing patterns and the failing pins of a fault, and this is obtained from the fault simulation. So the test failure need not be equal to the simulation. failure. So again, this we have two methods. The one is the static cause effect diagnosis, which does not change with the circuit and the diagnosis, CUD. And the other method is the dynamic. So this is the cause effect diagnosis, static or dynamic cause effect diagnosis. In this dynamic cause effect diagnosis, we here dynamic, what this dynamic word means is that fault dictionary changes with the TF, that is test failures. So now we will try solving one question. If we consider just the three faults for a circuit, which are say A is stuck at 1, J is stuck at 0, and Q is stuck at 1. We apply the three patterns, which are T1, which is 0, 1, 0, pattern P2, which is 0, 0, 1, and P3, which is 1, 0, 0, considering this. And if we consider that the good output is 1, 1, 0. So let's fill the fault dictionary table. Fault dictionary table. The pattern A stuck at the fault A stuck at 1, J stuck at 1, and Q stuck at 1. Pattern 1, pattern 2, pattern 3. So what is the circuit given to us is a gate level circuit combination. So this is E, this is G, means the fan after the fan of branch G. This is Q, H, J, and K. So what are the patterns? It's 1, 0, 1 second. I'll just draw this and we can write the pattern. First pattern is 0, 1, 0. Second pattern is 0, 0, 1. Third pattern is 1, 0, 0. And the fault 3, that is the good response, is 1, 1, 0. So now, if we apply the, okay, what are the faults that also you know? A stuck at 1, Q stuck at 1, J stuck at 0. Can I just select? Now we have to perform the fault simulation. So let's take a different color. Now I'm considering this is stuck at 1. So the pattern 1, this will become 1. This will be 1. So output this will be 1. And this is the fault free. This is, wait, sorry, this is already 1, 0, 1. So this is 1. This is 1. 1 up 0. This is an OR gate. For an OR gate, output is 0 if at least one of the output is 1. So this output is 0. So pattern 1, this it's given that the good output should be 0, but it is, sorry, 1, it is 0. So it's different. It can detect this. Now next pattern, next this one, this is also 1, this pattern. And this is 0, this is 1. So this is 1, this is 1. Again, this is 1. Any one of the input is 1, output is 0. So again, there is a difference. So this is also detected. So the next one is, this is 1, which is stuck at 1. So already no effect. And 0, 0 will give a 0 here, will give a 0 here. So this will be giving a 0. So again, this should be masked. Okay. This here you can observe that this fault is masked because it's already 1, stuck at 1. So this is masked. So it cannot detect this fault. So this pattern 3 cannot detect this fault. Okay. So the next I'll just keep one more copy of this circuit. Um, so this OR gate is 0, 0. So OR gate output should be 0. This should give 1. Is it? Yeah. So this is 1, this is 1. The 1, 1 will give 0. So this 0 and this 0 are same. So this fault, this pattern P3 is not able to detect the fault. Now we will go to the, so we said that this and this pattern can detect the A stuck at 1. Now we will see for the J stuck at 0. Okay, this is 0. Even in question this J stuck at 0. So now let's again apply and simulate it. So J means this. So till here 0, okay, 0, 1, 1, 1, 0, 1, 0. Okay. Anyone output 0, so it depends on the next output. So this is 0. Whatever is this sign. This means 0, 0 is 1. So this cannot be deducted. Next, similarly, 0, 0, 1 is 1 here, which is 0 here. And this one gives a 0 here. So you can see stuck at 0 and 0. So it cannot be deducted. Say next. 1 here, 0, 0 here, a 0 here gives a 0, which is a non-controlling value. This is 1, but it's a 0 because of stuck at 0. So 0, 0 is 1. So you can see this is different. So you can deduct this part. This was 1 and this was also 1. So now third one. So this is J stuck at 0. So this P1 and P2 were deducting A stuck at 1. P3 was deducting J stuck at 0. So now for Q stuck at 1, this is a Q stuck at 1. Let's simulate the patterns. So 0, what is 1 and 0? 1. This is stuck at 1. And this gives 1, 0, 0. Inverter 0, 0, 0, 1. So it cannot detect this for pattern P1. Next pattern, again 0. This is 1, stuck at 1. It cannot detect. Anyway, this is 0, so this gives. So we cannot detect. Next pattern. 1, 0, 0, which is 0, 0 here, a 0 here. Fault, no, 1 here. So this one is applied coming here. So this 0, 1 is 1. And any one of the input is 1. This is 1. Not 1, 0. Because this became the controlling input. So this fault cannot be detected by any pattern. So this is the fault dictionary. This requires the fault simulation. So any doubts? Yes. So if no doubts, then we can end today's section. Thank you so much for joining. So I'm ending the today's session and now I will stop the recording.